Answers to assignment questions. Question 38. Explain why, when temperature decreases, a balloon becomes smaller. When temperature decreases, the average kinetic energy of particles becomes less, and so the particles occupy less space. Separation between them decreases. That means the gas contracts, and so the balloon becomes smaller. By the way, particle never expands, nor contracts. It's only the gas, the liquid, or the solid expands or contracts. The next time when you use the kinetic theory to explain volume change, remember the sequence. First, the temperature change. Second, the kinetic energy of particles changes. Lastly, the particle will occupy more or less space. And finally, you may conclude that the gas, liquid, or solid expands or contracts. Question 39. There are two types of particle. Explain why the more massive particles vibrate less vigorously. The kinetic energy of particles increases with mass and speed. At the same temperature, different kinds of particles should have the same average kinetic energy. For a larger mass, the speed should be smaller in order to produce the same kinetic energy. For example, for helium gas molecule, the mass is 1 unit. The mass of oxygen gas molecule is 8 units. At the same temperature, if the speed of oxygen is v, then the speed of helium gas should be 2.82 v. And so helium gas molecules move faster. Question 40. Why we may compress gas, but we cannot compress liquid or solid? The reason is, there is large separation between gas particles, but there's not much between solid or liquid. Question 41. Why a lot of energy has to be supplied to vaporize a liquid, to turn it into gas? A lot of energy is needed to break the attractions between liquid particles. The attractions are very strong, and so a lot of energy has to be supplied there. This energy then becomes potential energy of the gas particles. By the way, kinetic energy of the gas particles may be the same as that of the liquid particles, because they may have the same temperature, as in the case of evaporation. Question 44. Explain how liquid in glass thermometer works in less than 25 words. At higher temperature, liquid particles vibrate faster, and so they occupy larger space. Therefore, the measuring liquid expands more, and the length of liquid column increases more. Many people just say when there is a higher temperature, then the liquid expands, and then finally the liquid column increases in length. But this is not enough. In order to measure different temperatures, the thermometer should give different readings. In particular, when the temperature is higher, then the temperature reading should be higher. Question 45. Why the liquid column of a liquid in glass thermometer does not increase in length forever when it is in hot surroundings? The liquid column does not rise anymore when the liquid is at the same temperature as the surroundings. In such a case, we say that they are in thermal equilibrium, so that there is no more heat flow from the surroundings to the thermometer. Question 46. In part A, you are asked to find the volume of liquid at 0 degrees Celsius. You can read it from the graph easily, and that is the volume in blue at the bottom right. And then you are asked to find the volume of liquid at 100 degrees Celsius. You may also read it easily from the graph, and that is the volume in red in the picture. In part C, you are asked to find the length h in the diagram, the increase in length when the temperature increases from 0 degrees Celsius to 100 degrees Celsius. That is, you have to find the volume, and after that, you may find the h. How to find that volume? Easy. How to find h? To find h, you have to divide volume by area. What area? This is the cross-section area of the capillary tube. So you may find the height h easily. For the last part, it is said that for the unmarked thermometer, the length is already 2.8 cm at ice water mixture, which is 0 degrees Celsius. 2.8 cm here. So what about the total length at 100 degrees Celsius? That is, you have to find this length. Do it yourself. Question 51. Why there is a lower limit of absolute temperature? Absolute temperature is a measure of kinetic energy. When the kinetic energy becomes 0, that is when all particles stop moving, then the absolute temperature should be 0. We call this absolute 0. At that time, particles are not moving at all. At a higher temperature, they move a bit. At even a higher temperature, they move more. Here comes the last question. Question 52. You are asked to plot a graph. First of all, let's start with the horizontal axis, temperature axis, then the vertical axis, volume axis. Plot the data points. Draw a straight line as close to the data points as possible. That's what it looks like. This question wants to tell you how the scientists find absolute 0. As temperature becomes lower, then the volume of a balloon becomes lower, and so the scientists deduce that at that very low temperature, the volume of balloon becomes 0. At that time, all particles stop moving. So what is the absolute 0 that you may find from this experiment? Should be about negative 275 degrees Celsius. Now let's move on to the pre-lesson video. Chapter 2. Internal Energy and Heat Transfer. Which object has more energy? An iceberg or a bucket of molten red-hot metal? When we talk about energy of an object, we talk about internal energy of the object. It is the sum of kinetic energy and potential energy of its particles. An iceberg has a huge number of particles. Although each particle does not vibrate too much due to the low temperature, the total potential energy and kinetic energy can be quite large. On the other hand, a bucket of red-hot molten metal does not contain many particles. Although each metal particle has a lot of kinetic energy, the total internal energy of the metal is smaller than that of a huge iceberg. 2.1. Mechanical energy of particles. Before we talk about mechanical energy of particles, let's first of all recall what kinetic energy and potential energy of a mass are. First, it is gravitational potential energy. The gravitational potential energy of a mass is higher if it is at a higher position. If she let go, then the mass goes down. At that time, the gravitational potential energy changes to kinetic energy of the mass. And that's why the mass speeds up when it falls. For a roller coaster on its rail, its potential energy changes to kinetic energy when it runs downhill. Its potential energy becomes smaller. At the same time, the kinetic energy becomes higher. Finally, at the last position here, on the right-hand side, you can see it has some potential energy, and it has also quite a lot of kinetic energy because it is at a low position. Simply speaking, when the roller coaster runs faster, it has more kinetic energy. When it is at a higher position, it also has a greater gravitational potential energy. Try these questions after the video. Chapter 2.2 Internal energy of an object, that is the total mechanical energy of its particles. As we said at the beginning of this chapter, the internal energy of an object is the sum of the kinetic and potential energy of all its particles. And of course, particles of an object also have kinetic energy and potential energy. The kinetic energy of particles come from their particle motions, and the potential energy of particles come from the force between particles, and that potential energy increases with the separation between particles. And so when particles move faster, then the average kinetic energy increases. This happens when temperature increases. On the other hand, when separation between particles increases, the potential energy of them also increases. And this happens when solid changes to liquid, or when liquid changes to gas. As you can see from these pictures, the particles are very close together when they are in solid form, and then they become a little bit further away from each other when they are in liquid form. Finally, in gas form, the particles are very far away from each other, so we can see that the potential energy increases when solids melt to become liquids, or when liquids vaporize to become gases. But note that the kinetic energy of particles and kinetic energy of an object are different. The kinetic energy of particles is due to the motions of the particles, but the kinetic energy of an object is the motion of the object itself. So let's take a look at these two examples. On the left, it is a pot of boiling soup. The kinetic energy of particles are high because the temperature is high, but the kinetic energy of the water as an object is low because the water does not move. It is inside a pot. Now let's also take a look at the water tank truck on the right hand side. The truck is moving, so the kinetic energy of the truck is high. But talking about the kinetic energy of the water inside the truck, it is low because the water has a low temperature. Similarly, for potential energy, the potential energy of particles on the left hand side increases from solid to liquid to gas. But talking about gravitational potential energy, they are about the same because they are all on the same level. On the other hand, on the right hand side there is a snowball at the top of a cliff, and it has a high gravitational potential energy, but its particles have low potential energy due to the low temperature. Try to fill in blanks questions after the video. So let's start the second part, which is the more important part of today's lesson. 2.3 Heat and energy transfer. If you put your fingers near a hot iron or even touch it, then you feel hot because there's heat energy that flows from the iron to your finger. In fact, there's heat flow between the fingers and the iron due to the temperature difference. The heat will flow until they have the same temperature, and at that time we say there is thermal equilibrium between the finger and the iron. So if you drop a piece of metal at 70 degrees Celsius into a beaker of water at 5 degrees Celsius, then their temperature will finally become the same, as there is heat transfer between them, until finally there is thermal equilibrium. So you see that heat transfer is due to temperature difference. And the energy that transfers from the hot object to the cold object is called heat energy. And the process, heating. There are two common methods in physics for heat transfer. One is by heating, such as using an immersion heater. The other is by doing work, which makes use of the work done against friction, such as when you rub your hands. Do these questions after the video. This is the last part of the video. 2.4 Power. Rate of energy transfer. We may use an immersion heater to transfer heat from the heater to the water, and usually the energy is transferred at a constant rate, which means a constant amount of energy is transferred from the heater to the water. For example, a 30 watts heater transfers 30 joules of energy to its surrounding in each second. W stands for watt, which is the unit for power. And you can see the power of an immersion heater tells you how much energy can be transferred in each second. The electric kettle here in the diagram is a more powerful heater. It can transfer 2,200 joules of energy to the water in 1 second. So, as you can see, if you are given the power of an electrical appliance, then you may know how much energy it may transfer. For heating, and you may use equation 5 here, where Q stands for energy supplied, and P stands for power, and T stands for time of heating in seconds. For example, for the electric kettle, which has a power of 1,500 watts, heating for 7 minutes, altogether there is 560 seconds. Multiply with the power 1,500, and you may see there is a huge amount of energy, which is 630,000 joules of energy transferred from the kettle to the water. In this way, if you know the power of the electric kettle and the time of heating, then you may calculate the amount of energy transferred easily using equation 5 above. On the other hand, you may also measure directly how much energy is transferred by using a joule meter. And next time in the physics lab, your physics teacher will show you this setup. There's a joule meter, and we connect this to an immersion heater. The amount of energy used by the heater can be found easily from the joule meter. However, the joule meter reading does not go back to 0 itself. You have to mark down the initial reading before you turn on the heater. And when you turn off the heater, you may then mark down the final reading. And the difference of the two readings tells you how much energy is transferred by the heater. And one very important thing when you are using an immersion heater. When an immersion heater is heating some water, for example, we can find that the temperature increases linearly with the energy supplied. As we heat, the temperature increases linearly along a straight line. And what is interesting is, when the heater is turned off, the temperature keeps rising. Why? Because the heater is still hotter than the water at the time when you turn it off. So it takes time for thermal equilibrium between the heater and the water. That's the end of the video.